With these problems, try to work them out before you look at the solutions. So stop the video and see if you can solve this problem, and then we can work it together. A baseball diamond is a square with sides 90 feet. A batter hits the ball and runs towards first base with a speed of 24 feet per second. At what rate is his distance from second base decreasing when he is halfway to first base? Okay, let's look at our given information. So given, it says the batter hits the ball and runs towards first base with a speed of 24 feet per second. So we could say dB dt equals 24 feet per second. Now we need to identify what is B. What does B represent? The batter hits the ball and starts running along first baseline. So let's say the batter is here. I'm going to define B as the distance the batter is from first base, not from home. You could solve this problem and say I'm going to define B to be the distance from home plate to the batter, and that's fine. Your problem will look a little bit differently, but you could solve it that way. But I'm just going to solve it this way. dB dt then is 24 feet per second. Now what are we trying to find? Now we could list also on our diagram, since we are looking at the distance the batter is from second base, we could say, well, we know the distance from first base to second base is 90 feet. So if we wanted to list that, that's fine. Now, what are we trying to find? It says a batter hits the ball and runs towards first base with a speed of 24 feet per second. At what rate is his distance from second base decreasing when he is halfway to first base? So we are trying to find the rate at which this distance from the batter to second base is decreasing. I'm going to label that as x. That distance is x. So we are trying to find dx dt. Again, we need to find this distance, this rate of change of distance at a particular instant. So when are we trying to find this? Well, it says when he is halfway to first base. So B would equal 45. The distance from the batter to first base, if he's halfway, would be 45 feet. So let's look at our equation. So the equation that's going to relate these variables, b and x, together would be the Pythagorean theorem. So we would have b squared plus. Now if you look at our triangle, notice this side is always 90. No matter how far the person is, the batter is from first base, which is our b, and no matter the length of x. Those two are changing. But this side from first to second base is 90, and it doesn't change as the batter is running to first base, like b and x are changing. So at this point, we can just say that is a constant. So we can just plug in 90. So 90 squared equals x squared. So we're going to now find our related rate equation. So we'd have 2b dB dt. Now the derivative of 90 squared is 0. So we'd have 2x dx dt. What information can we now plug in? We do have b, so we can say 2 times 45 dB dt is 24 feet per second. And now we need to find x because we are trying to solve for dx dt. So if we can find x, we can solve this problem. So going back to our diagram, if we have this triangle, we know at the instant we're looking for dx dt that this would still be 90, but this would be 45. And so now we should be able to find the value of x when one side is 90 and the other is 45. So if we looked at the Pythagorean theorem, we'd find x equals 90 squared plus 45 squared, and we would get 45 times the square root of 5. So now we have our value to plug in for x. So we'd have 2 times 45 times the square root of 5 dx dt. And now we can solve for dx dt. So dx dt, you would divide both sides by 2 times 45 times the square root of 5. And you would get the distance from second base is decreasing at a rate of 10.7 feet per second. Now, notice on this one that I could have said that dB dt is negative 24 feet per second, and then we would have ended up with an answer that was negative. See here, we would have got negative 10.7 feet per second. But I'm saying, since I left it positive, I'm saying this is decreasing at a rate of 10.7 feet per second. A television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation S equals 50 t squared, where S is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change in the angle of elevation of the camera at 10 seconds after liftoff. So try to work through this problem. All right, let's look at our given information. It says we have a position equation of S equals 50t squared. Let's go ahead and list that as given information, where S is measured in feet, t is measured in seconds. The camera is 2,000 feet from the launch pad, and we do have that indicated in our diagram. So it says find the rate of change in the angle of elevation of the camera 10 seconds after liftoff. So we are trying to find the rate of change in the angle of elevation. So that would indicate we're trying to find that angle. So we're looking for the rate of change of that angle with respect to time. Now, when are we trying to find that? We are trying to find this, it says, when t equals 10. So 10 seconds after liftoff. So what's an equation that we could use to relate our variables together? Now we know the position function of the rocket. It says that's the position function, S equals 50t squared. So how could we relate our variables together here? S are theta, and we know this is the angle here. So we would probably say, since we have the opposite side of the angle and the adjacent side of the angle, we probably are going to use our tangent. So we would have the tangent of theta equals S over 2000. So finding our related rate equation, we take the derivative, secant squared theta times d theta dt, and this would be 1 over 2000 times our ds dt. Looking at the triangle, we have this side is 2000. This is our angle that we are looking for. So we need to be able to find the secant of this angle. Now, in order to find the secant of the angle, we need to find one more leg of this triangle and then find the third leg possibly, because it appears that we can find the opposite side and then we would need to find the hypotenuse. Now, how could we find the opposite side of the angle? Well, it says that we're trying to find d theta dt at 10 seconds. So we should be able to determine, since we have the position function of the rocket at 10 seconds, we should be able to find that distance that it's traveled in 10 seconds. So if we plugged in to our position function, S equals 50 times 10 squared, that should give us the distance it has traveled in 10 seconds. So we should have 5,000. All right, now we should be able to find the hypotenuse of this triangle. So the hypotenuse, we would have 2,000 squared plus 5,000 squared. And let me find my calculator here so we could take 2,000 squared. We get 4 million. And if we take 5,000 squared, we get 25 million. So we would have the square root of our 5,000 squared plus our 2,000 squared would be the length of our hypotenuse. So that would be this quantity here plus our 5,000 squared. So now we have the value for secant theta. So we could plug that in here. So we could say the secant of this angle, I don't know if I can fit it in down here. It's probably not going to let me write that down there. So the secant of our angle is hypotenuse. So we have the square root of 2,000 squared plus 5,000 squared all over the adjacent 2,000 squared. And that's finding this quantity here. And d theta dt, that's what we're trying to solve for. So we'll still have our d theta dt equals 1 all over 2,000 times ds dt. And ds dt, if we looked at back here at our given, we have s. So ds dt would be 100t. Well, we want to know the instant the angle is changing at 10 seconds. So we would plug in 10 for t in our ds dt to get 1,000. So we'd have times 1,000. So now we could solve for our d theta dt. So if we calculated that out, we would get 2 over 29 radians per second. It's not going to let me write 29. So the answer we said is 2 over 29 radians per second. Let me see if it will go this way. And that would be rads per second. A water tank has the shape of an inverted circular cone with a base radius 2 meters and the height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per second, find, should be a comma there, find the rate at which the water level is rising when the water is 3 meters deep. So we have a radius here of 2 meters and a height of 4 meters. So what is our given information? We have water is being pumped into the tank at the rate of 2 cubic meters per second. That is changing our volume. So that would give us a rate of change of our volume of 2 cubic meters per second. Okay, what are we trying to find? We are trying to find the rate at which the water level is rising when the water is 3 meters deep. So I'm going to call this H. So we're trying to find the rate of change of the height of the water level And when are we trying to find that? When h equals 3. So what is our equation? Well, for this problem, we're trying to relate V and H, so we are working with an inverted circular based cone. So we would look for the volume of that, which would be volume equals 1/3 area of the base times our height. Now, if we were to take and differentiate both sides of the equation, do you see that we would have an R and an H on the right side? We'd have to apply the product rule. It might get a little bit messy. We may be able to work around that. Let's go back to our diagram. We have our cone. We said the radius is 2 and the height is 4. And here's the height of the water, let's say. We said that was h. And so I'll call this little r here, the radius of the water. And that's what is represented in our equation. R and h is the height of the water and the radius of that column of water, not the whole cone. Now, the idea here is, can we create an equation that relates R in terms of H so we can replace either R or H and only have one variable on the right side? Then we don't have to use the product rule. Well, if we looked at our diagram, we may see that we have two triangles, and they are similar triangles. This big triangle here, and then the smaller triangle here. So those are similar triangles. So we could say R is to H as 2 is to 4. And since we are trying to find the rate of change of the height, we don't want to lose that. So let's solve for R so we can replace R in our equation in terms of H. So R would equal, I'm just going to multiply H to both sides and reduce 2/4 to 1/2. We'd have H over 2. Now back in our equation here, we're not going to take the derivative yet. We're just going to make this substitution. We said R equals H over 2. So we're going to replace R with H over 2. And now we only have one variable. We only have h on the right side. So we'd have pi over 3. And if we multiplied this out, h over 2 squared is h squared over 4. So we'd have h cubed over 4. And again, we haven't found the derivative yet. We're just simplifying our equation. So this would be pi over 12 times h cubed. Now, that is going to be much easier to work with. So we have our volume equals pi over 12 h cubed. Now we can find our related rate equation. We would get dv dt equals, now we bring the 3 down, so we'd have 3 pi over 12 h squared dh dt. And you can see we haven't lost our dh dt. If we would have solved for h in terms of r and replaced h, well, then we wouldn't have our dh dt in the equation. That's why we solve for r in terms of h. Now, plugging back in the information that we have dv dt equals 2, and reducing this by a factor of 3, we'd have pi over 4. Now, when are we trying to find dh dt? Well, back here we have listed, we're trying to find dht when h equals 3. So we would plug 3 in, and now we can solve for dh dt. So our dh dt would equal. Now we can just figure that all out and come up with 0.28 meters, and our units were minutes, meters per minute. And there we have our answer, dH dt.